Yep. Thank you for introduction. Uh, Good afternoon, everyone. Usually after lunch, I'm very sleepy. If you nearly fall asleep, I will not ask you a question, blame you. Okay, let's start. It's about the thermal analysis of the railway brake disc. My supervisor is William and Spencer. And very quickly, okay, please read. Short introduction about our group. Uh, we're from the vehicle engineering and mainly focus on the vehicle dynamics. And the university in Stockholm is not far from here, 400 kilometer. The agenda for today is mainly four part. And first we go to the introduction, why we do this project. Uh, all the vehicle need to change the speed or stop. So the braking is important. And the braking is a process that kinetic energy of the vehicle converts to the other forms like electricity or the thermal energy. And the mechanical brake is mainly based on the friction brake pattern. They have the relative motion. And then this relative motion will generate brake force and also generate thermal energy. So the temperature of the brake disc or the wheel will increase. And this high temperature, it will reduce the coefficient of friction and also will damage the brake disc. And so the aim of the most research related to this area is to reduce the maximum temperature of the brake disc as low as possible. And so the first step is we need to know that how to get the accurate disc temperature. Experimental is quite um, expensive, and usually the driver need to know the temperature of the brake disc because if the temperature is very high, then the driver need to start the braking very early. So how to get this temperature? There are mainly two method. One is very roughly according to the energy transformation, like the 95% of the kinetic energy directly transferred to the thermal energy. And another way is based on the more detail, like the calculate the contact pressure, contact area. And this part, most starting in this part, they always assume the constant contact area. Uh, but from the point of the tribology part, the disc and the brake pad, it seems they are contact each other, but they are only around 20% real contact. So that we define our research question, what is the influence of the contact area on the temperature of the brake disc? Most research, they always assume the 100% contact. And if we try the 20% contact, what will happen? And then go to the method part. Um, this is the 3D and the transit simulation. And all the friction heat is generated from the contact surface of the rubbing element and the surface of the brake disc. When they contact each other, then will generate the friction heat. And also we consider the radiation and the convection. Then this is the modeling part. There's a backward and a forward method. We want to use both of this method to compare, but until now we're still in the implicity part. And we can see the bilinear form of the implicity part is quite a lot of the items, and the explicit method is quite short. It's only one item, and that is our defined finite element questions. Yeah, and then we go to the difficult part of this project, the braking process. The brake disc or the wheel is always rotating. And in here, we use the same skill like in the morning. I think there is one presentation about the gear. The gear is fixed in there and apply the boundary conditions, move in the boundary part. And here it's a same. Our contact area is this colorful, different colorful part, the rubbing element part. And because the brake disc is moving, and so this heat flux import part should also move. And here we need, for this time step, the import heat flux is here, and the next step will be more to here than to here. If we go next step, yep. So all the focus is in that Newman boundary condition part, the heat flux part. So that in each time step, we will update the Newman boundary condition applied part. We will find that location, the contact location, and it's every time it's a new place. And thanks to a G mesh that we can know the every node's name, then we can find, okay, in this time step, in this part, we import a heat flux, and the next step, we go to another place. So we can control nearly everything. And since we are engineering, we are related to the brake is quite important. So we have to do the experimental test to show that our simulation is reliable. And all the simulation and the experimental are according to the international standard. There is all very fixed procedures. And then is the result and the discussion part. Through this animation, it seems good that temperature is increased. All this is a temperature, and it seems the brake disc temperature slowly increase. But then, if we go to the compare with the experimental, okay, it's a large difference. This part it should be the mesh element size. The fourth step, what we do is mesh independent analysis. That's a different mesh size. It should not influence a temperature very significantly. But here, we increase the mesh element number or reduce the size of the mesh. It seems the result is still not converged very well. But the general trend compared with the experimental, it looks okay. But this initial simulation results still could we still could find something useful, like for the average temperature of the brake disc, different contact area, the influence to the average temperature is only very small. It's only 10 degrees Celsius, but for the maximum temperature, it's 108 degrees Celsius. So we could get a conclusion that for the maximum temperature of the brake disc, the contact area is quite important. Previously, that many people assumed 100% contact part. That is not good. And for the future development, we need to do more effort on the mesh sensitivity analysis because still the result is not converged very well. And we try the other elements. And until now, we are only in the heat transfer equation part. We haven't been to the elasticity. We got the deformation of the brake pad and the disc. And Yes, this part is mainly the temperature will influence the strength, thermal strength, and then they can connect together. That is the work I'm doing now. And later, maybe we go to Navier-Stokes equation. We can got the velocity of the air, and then that will influence the heat transfer coefficient. Okay, this is a conclusion. And previously, I used the Ansys mechanic. I used 1.5 years to do this research, and we have some results already, but then asked a lot of questions. A lot, it's feeling a little like a black box for me, this commercial software. And I asked a lot of questions, and later maybe they don't like me, and then they don't reply very quickly. And and then I come to the Phoenix open source code. It's giving me a lot of the freedom. Yeah, and thanks you all. Yeah.